here's something that'll mess with your head. You take a piece of ordinary glass, like your window, and shine light at it. Most of the light passes through, but exactly 4% bounces back. 4 out of every 100 photons hit that surface and just turn around. Now here's the part that should keep you up at night. How does a photon decide? Think about it. You've got 100 photons, completely identical, all hitting the exact same piece of glass at the exact same angle. 96 go straight through. 4 bounce back. What makes those 4 special? Your first instinct might be to think there are imperfections in the glass, little rough spots that reflect, tiny gaps that let light through. That's perfectly reasonable, except it's completely wrong. You can polish glass until it's flawless at the atomic level, perfect surface, no defects whatsoever, and you still get exactly 4% reflection every single time. The photons aren't bouncing off imperfections, so what are they bouncing off? Maybe the photons themselves are different somehow. Maybe they have internal properties we can't see, little spinning wheels or hidden clocks that determine their fate. Sounds crazy, but honestly, it's not the worst idea. Except, there's an experiment that completely destroys this explanation. Take a very thin layer of glass. Now you've got 2 surfaces instead of 1, a front surface and a back surface. If each surface reflects 4% independently, simple math says you should get about 8% total reflection, 4% from the front, roughly 4 from the back. But that's not what happens, not even close. Depending on exactly how thick that glass layer is, you can get anywhere from 0% reflection to 16% reflection. 0 to 16. The same glass, the same light, just different thicknesses. And the reflection swings wildly between nothing at all and quadruple what you'd expect. How is that even possible? How can adding a second surface sometimes cancel out the reflection from the first surface completely? It's as if the back of the glass is reaching forward through time, telling the front surface, don't bother reflecting this one. And if you keep making the glass thicker, the pattern repeats over and over again, perfectly regular, like clockwork. With really precise equipment, you can watch this pattern continue for millions of cycles. This isn't some tiny anomaly or measurement error. This is fundamental to how light actually works. So what's really going on here? Here's where it gets genuinely strange. The explanation that works, the only explanation that matches every experiment we've ever done, is that light doesn't pick one path. It doesn't decide whether to reflect or pass through. Instead, and I know this sounds absolutely insane, light takes every possible path simultaneously. When a photon approaches that glass, it doesn't choose, it explores all options at once. It reflects from the front surface and passes through, and reflects from the back surface and passes through both. All of these possibilities happen together at the same time. Now wait, if everything happens, why do we see definite results? Why does the detector either click or not click? Here's the key. Each possible path carries what physicists call a probability amplitude. Think of it like a little arrow pointing in some direction. When you add all these arrows together, the ones pointing the same way reinforce each other. The result gets bigger. The ones pointing opposite ways cancel each other out completely. So when light goes through thin glass, the arrow from reflecting off the front and the arrow from reflecting off the back might point in the same direction. Add them up and you get a big arrow, high probability of reflection, 16% instead of 8. But if the glass is slightly thicker or thinner, those arrows might point in completely opposite directions. They cancel perfectly, 0 reflection. The light from the front and the light from the back literally eliminate each other through interference. And here's what you need to understand. This isn't just about glass. This is everything. Mirrors, lenses, rainbows, the blue color of the sky, why metals are shiny, why water is transparent, all of it comes down to these little arrows adding up or canceling out. All of it requires that light explores every possible path at the same time. The theory that describes this is the most precise theory in all of science. It makes predictions accurate to 12 decimal places. If you measured the distance from Los Angeles to New York, this theory could tell you the answer to within the thickness of a human hair. That's how absurdly good it is.
But here's the thing that haunts physicists. Ask any one of them to explain why light behaves this way, why it explores all paths, why probability works through these little arrows. They can't tell you. Not because they're not smart enough or haven't thought about it. Generations of brilliant people have tried. The answer is simply, we don't know. Nature just works this way. Let me show you how deep this goes. Think about a regular mirror. You probably learned that light bounces off according to a simple rule. Angle in equals angle out. That's true. But why? The explanation you probably heard is that light travels in straight lines and bounces like a ball. Simple, right? Wrong. Light actually bounces off every part of the mirror, not just the middle spot where the angles match. Every single part. The edges, the corners, everything. The light bouncing off the far left edge of your mirror is absolutely real. It's happening right now. So why do we only see the reflection from the center where the angles match?
Because of those arrows again. The paths from the middle of the mirror all take roughly the same amount of time to travel from the source to your eye. Their arrows point in similar directions. They add up, they reinforce. But the paths from the edges take very different amounts of time. Their arrows spin around and point every which way. One edge contributes an arrow pointing up. The next spot over contributes one pointing down. They cancel. The contribution from the edges just disappears. You can actually prove that light bounces off the edges. If you take a mirror and very carefully scratch away parts of it, not randomly, but in a precise pattern, removing only the parts that contribute arrows pointing in the wrong directions, suddenly the edge of the mirror starts reflecting like crazy at angles that should be completely impossible. This is how a diffraction grating works. It's literally just a mirror with most of it blocked off in a clever way so the cancellation doesn't happen anymore. Light doesn't know the law of reflection. It doesn't know that angle in should equal angle out. It just goes everywhere, and the mathematics makes it look like there's a simple rule. Now we need to go deeper, because light does more than just bounce around. It interacts with matter, with electrons. And this is where things get even more absurd. In the entire universe, when it comes to light and matter, there are only two kinds of particles that matter. Photons, particles of light, and electrons, particles of matter, the things that make atoms work. That's it. Two players. And everything you see around you comes from these two particles doing a very simple dance. There are only three things that can happen. First, a photon travels from one place to another. Second, an electron travels from one place to another. Third, an electron absorbs or emits a photon. Three actions. That's the complete list. Everything else is just combinations of these three things happening over and over in different arrangements. When you see a red apple, what's actually happening? Photons from the sun hit electrons in the apple's surface. Those electrons absorb the photons, jiggle around, and emit new photons. Red photons get emitted more than blue ones because of how the electrons in that particular molecule are arranged. Those red photons travel to your eye, hit electrons in your retina, get absorbed, and trigger a chain of events that eventually becomes the experience of seeing red. Every step, photon moves, electron interacts with photon. Over and over and over. Each of those three actions has a probability amplitude, one of those arrows. And here's where it gets really strange. The arrow for the interaction, when an electron emits or absorbs a photon, is always the same size. Always, no matter what. It's a single number, roughly 0.1. Or if you want to think about probability, you square it and get about 1%. 1 in 100. This number is one of the most mysterious things in all of physics. It shows up everywhere. It determines how strong the electromagnetic force is. It controls how atoms hold together. It sets the scale for all of chemistry. And nobody, absolutely nobody, knows where it comes from. You can measure it incredibly precisely. It's approximately 1 divided by 137, or about 0.0073. Physicists call it the fine structure constant. If you ask why it has that value instead of some other value, you get silence, confused looks, maybe some speculation, but no answer. It's like asking why the speed of light is what it is, or why the electron has the mass it has. These are numbers we can measure, but cannot explain. They're just facts about the universe, brute facts with no deeper reason that anyone has found. So we've got these 3 actions and their arrows. To figure out what actually happens in any situation, you do something remarkable. You draw pictures, very specific diagrams showing all the possible ways something could happen using just those 3 basic actions. A photon goes here, hits an electron, the electron moves, emits a photon, that photon goes somewhere else, every possible sequence. Then you calculate the arrow for each diagram by multiplying together all the individual arrows. Photon travels, multiply by its arrow. Electron travels, multiply by its arrow. Interaction happens, multiply by 0.1. After you've got all the diagrams and all their arrows, you add them up. Some reinforce, some cancel. The final arrow you get, you square it, and that's your probability. Every time you have an interaction, you multiply by roughly 0.1. So a diagram with 1 interaction has a factor of 0.1. 2 interactions, 0.01. 3 interactions, 0.001. The more complicated the diagram, the smaller its contribution. This is why physics can make predictions at all. The simplest diagrams matter most. The complicated ones contribute less and less. You can ignore most of the infinite possibilities because their arrows are too tiny to matter. But you can't ignore all of them. When you add up thousands of these tiny corrections, the predictions match experiments to 12 decimal places. No other theory in all of science comes close to this level of accuracy. Here's something that seems like it shouldn't work, but does. In these diagrams, photons can do things that seem impossible. They can travel backwards in time. They can go faster than light. They can have negative energy. How can that be allowed? The key is that these weird photons never get observed directly. They're called virtual photons. They exist only as intermediate steps in a calculation. A real electron over here emits a virtual photon. That virtual photon does something impossible, like traveling backwards in time. Then another electron absorbs it. The end result is just 2 electrons pushing each other apart. You never see the virtual photon. You can't catch it with a detector. It only exists mathematically. And here's what's wild. You have to include these impossible paths. If you only counted the sensible-looking diagrams, you'd get wrong answers. The theory only works when you let photons do crazy things in the middle of the calculation, even though the final answer always describes something perfectly reasonable. This is what physicists mean when they say nature is absurd. Not absurd in a random way, absurd in a very precise, very specific way that gives exactly correct predictions. Why these rules? Why does the interaction strength have that particular value? Why do the arrows add the way they do? Why does probability come from squaring the arrow instead of cubing it or taking the absolute value? Nobody knows. These questions have been asked for almost a century. The best minds in physics have wrestled with them, and we're no closer to answers than we were at the beginning. The theory works. It's the most successful theory humans have ever created, but understanding why it works, that's still out of reach. There's a certain kind of honesty in admitting this. Science isn't about pretending to know everything. It's about being precise about what we do know and clear about what we don't. We know how light behaves. We can calculate it with extraordinary precision. Why it behaves that way, that's still a mystery. Maybe someday someone will figure it out. Maybe the answer is waiting in some equation nobody has written yet. Or maybe some things just are the way they are.
Let's bring this all together, because there's something deeply unsettling about what we've discovered. The world we see, solid objects, definite events, light traveling in straight lines, that world is a kind of illusion. Not an illusion in the sense that it's fake, it's real, but it emerges from something much stranger underneath. Underneath, there are no straight lines. There are all lines, every possible path happening together. Underneath, there are no definite outcomes until something is measured, just amplitudes, just possibilities all superimposed. The classical world we experience is what you get when trillions upon trillions of these quantum events average out. The arrows pointing in every direction mostly cancel. What survives is the sensible-looking stuff, the stuff that matches our intuition. But that intuition is just a consequence of scale. This isn't a limitation of our knowledge. It's not that we haven't figured out the deeper mechanism yet. As far as anyone can tell, there is no deeper mechanism. The quantum level is the bottom. The arrows, the interference, the probability, that's what reality actually is. You might think, okay, but surely there's some hidden variable we haven't found, some underlying clockwork that determines which photon reflects and which passes through. People have looked for almost 100 years. They've done incredibly clever experiments designed to catch nature hiding information from us. And every single time, nature isn't hiding anything. The randomness is real. The probability is fundamental. There's no secret script determining outcomes in advance. This was hard for a lot of physicists to accept. Some of the greatest minds of the 20th century spent decades trying to find a way around it. They couldn't. Not because they weren't smart enough, but because there doesn't seem to be a way around it. This is just how reality works. Physics gave up on something profound. It gave up on the idea that we can, even in principle, predict exactly what will happen. The best we can do, the absolute best, with perfect knowledge of everything, is calculate probabilities. That's it. That's the ceiling. And the theory that accepts this limitation is the most accurate theory humans have ever produced, by a huge margin. It's not even close. There's a tendency to believe that science explains things, that when you really understand something, you can say why it happens. But that's not quite right. Science describes things. It tells you how things behave with incredible precision, but the why questions often don't have answers. Why does the interaction between light and matter have strength 1/137? Nobody knows. Why do the rules of quantum mechanics look the way they do instead of some other way? Nobody knows. These aren't questions that science has failed to answer. They're questions that might not have answers at all. Or if they do have answers, those answers might just push the mystery back one level. You explain this in terms of that, and then you have to explain that in terms of something else. Eventually, you hit bottom. You reach the place where the only honest thing to say is, this is just how it is.
You have to be comfortable with that. Actually comfortable. Not fake comfortable where you pretend the question doesn't bother you. Because the universe doesn't owe us explanations that fit our intuitions. It doesn't owe us answers that feel satisfying. It just does what it does. And our job is to describe that as accurately as possible. The strange thing is, once you accept this, the weirdness becomes kind of beautiful. Light exploring all paths at once isn't just bizarre, it's elegant. All of chemistry and biology and material science emerging from three simple actions isn't just surprising, it's profound. The fact that we can predict anything at all in a universe this strange is remarkable. This picture of reality, with its probability amplitudes and interference and particles doing impossible things when nobody's looking, it didn't come from philosophy. It didn't come from pure thought. It came from experiments. People measured things, found results that didn't make sense, and were forced to invent new concepts to describe what they saw. Nature dragged us kicking and screaming to this understanding. We didn't want quantum mechanics. We didn't ask for probability to be fundamental, but the experiments left no choice. That's how science works. You don't get to pick what's true. You follow the evidence wherever it leads, even if it leads somewhere uncomfortable.
We have a theory that works spectacularly well. A theory that says light is both simpler and stranger than anyone imagined. 3 actions, little arrows, interference. That's enough to explain every optical phenomenon ever observed. Every color, every reflection, every rainbow, every laser. But we don't understand why this theory is true. We don't know where the rules come from. We don't know if they could have been different, or if there's some deeper principle that makes them inevitable. And maybe that's okay. Maybe the honest answer is we're still figuring it out. Science isn't finished. It might never be finished. There might always be another layer, another mystery, another question we can't quite answer yet. But look how far we've come. 100 years ago, we didn't even know light came in particles. Now we can predict its behavior to 12 decimal places. We can build lasers and fiber optics and technologies that would have seemed like pure magic to earlier generations. The universe is stranger than we ever imagined. And somehow, against all odds, we're starting to figure it out. Not by imposing our ideas on nature, but by listening carefully to what nature tells us through experiments, even when what it tells us seems impossible, even when it violates everything we thought we knew. That's the real miracle here. Not that reality is strange, but that human beings, with our limited brains evolved for hunting and gathering on the African savanna, can understand it at all. We might never know why the universe works the way it does, but we're learning how it works with extraordinary precision. And in a universe this vast and mysterious, maybe that's enough.